Hello, oceanography class. Let's go over Chapter 6, Air-Sea Interaction. The themes here really are kind of understanding that our atmosphere and oceans are two separate portions of the dynamic Earth system, but that they influence each other. And when one is altered or changed, it's going to alter or change the other system. They're interconnected. And what really starts all the motion in the atmosphere and wind generating low pressure or high pressure systems, changes in density, is solar energy, and that heats up the Earth, and that's what generates the winds. And then those winds are what push on the surface of the ocean, and that's what drives ocean currents. And then there are extreme weather events that occur, hurricanes as an example, massive low pressure systems that kind of spiral out of control. They're related to ocean currents and ocean temperature, where they form. And global warming is affecting our oceans in a number of ways, one of which is putting a lot of carbon dioxide, dissolved carbon dioxide, into the water. But it's warming the oceans. And when you have warmer oceans, that has the tendency to intensify hurricanes. And so that's how it's related to our atmosphere retaining more heat, heating up the oceans, and then driving extreme weather events. All right, so let's talk about Earth's orbit. Its orbit around the sun. The sun is what generates energy, and then it hurls that energy towards the Earth. Okay, our orbit is slightly elliptical, meaning that now this is not to scale, this is just to show you the difference. This dashed line here is a circle, perfect circle surrounding the sun, as if we orbited in a circle, but we don't really orbit in a circle, we orbit in an ellipse. And what that means is there are certain times in our orbit where we're closer to the sun, like over here, and other times when we're further away from the sun. And that affects how much solar energy our Earth receives. So it's important to consider that. But this doesn't cause our seasons, meaning like fall, winter, spring, summer. Our seasons are the direct result of our tilted axis. Okay, so if you look at our Earth as a globe, our axis, an imaginary line that goes through the center of a sphere, right, comes out the other side over here, is not just straight up and down. It's actually tilted about 23.5 degrees, and that's to the respect of the plane of the elliptic, and that's the plane, an imaginary plane that kind of goes through the center of our Earth and the center of the sun. Okay. Now what happens is, as we orbit the sun, which takes 365 days, the tilt of our, you can imagine the Earth spinning in a counterclockwise direction like this. Sometimes the northern hemisphere will be tilted towards the sun, and in this example over here, in this part of our orbit, the northern hemisphere is tilted away from the sun, and that affects how much solar energy each one of the hemispheres receives in different portions of its orbit. Okay, and so what that essentially means is if we're in this part of our orbit and the northern hemisphere is tilted away from the sun, that means the northern hemisphere is experiencing winter. On the other side of the Earth, the southern hemisphere, you can't really see it here, but it's tilted towards the sun, and they're experiencing summer. Okay. If we go over here, the northern hemisphere is tilted towards the sun, so you can imagine the Earth spinning in this direction. The northern hemisphere would be receiving more solar radiation, and then therefore northern hemisphere is experiencing summer. While the southern hemisphere down here is tilted away from the sun, they receive less solar radiation and they experience winter. Okay. Here you can imagine, you can go down here. This is the example of the northern hemisphere pointing towards the sun, and you can see that more of the northern hemisphere is receiving more solar radiation throughout a day during the summer. So just imagine this globe spinning in a counterclockwise direction. Okay. Oops, excuse me. I can't erase this. Sorry. This area here, this is the part of the Earth that wouldn't be facing the sun and would be experiencing nighttime. When the northern hemisphere is facing away from the sun during the northern hemisphere winter, you can see most of the northern hemisphere here is experiencing nighttime, and just the days are very short as we kind of rotate in and out of that line of illumination. And then there are two interesting times in our orbit: the vernal equinox, which falls around March 21st, and the autumnal equinox, September 23rd, typically. And what happens here is that the line of illumination happens to go directly from the geometric pole to pole. And what that means is the entire Earth experiences a day with 12 hours of sunlight and 12 hours of nighttime. So, and that happens twice a year, during the spring and during the fall. Okay. And just so you know as well, when we're in our northern hemisphere summer, so in this situation here, our days are longer. I don't know if you've noticed this, but days, or the amount of sunlight hours, hits a maximum during the what we call the summer solstice, which would be the longest day of the year. And that is typically around June 21st. And then our shortest day of the year is the winter solstice, which occurs around December 22nd. So that's the depressing day when you're at work all day. You wake up in the morning and it's dark, and then you work all day. And by the time you get out, 4 o'clock, 5 o'clock, let's say, it's still, there's the sun has gone down already, so it's darkness. And it gets worse and worse the further you go, or the higher latitudes. When you're closer to the poles, that change is more dramatic. In fact, if you're close enough to the poles, during the winter, it's dark 24/7, which is very depressing. But in the summer, if you're near the poles, you'd have 24 hours of sunlight, which is pretty crazy. So what happens is the sun kind of looks like it's going to set in the horizon, but then it starts rising up again. And so essentially the sun never goes down. Essentially the Earth never rotates away from the sun during that time. So here are those special days we've talked about: the vernal equinox, autumn equinox. Okay. Then there's the summer solstice, longest day of the year in the northern hemisphere, and that's when the sun is directly above the Tropic of Cancer, which is about 23.5 degrees. And then there's the winter solstice, the shortest day of the year in the northern hemisphere, and that's when the sun is directly over the Tropic of Capricorn in the southern hemisphere, 23.5 degrees. And so that's the reason why we have seasons on Earth, and it's just basically because we're tilted 23.5 degrees away from the sun and towards the sun, depending on where we are in our orbit. Okay. So the region between the latitudes of 23.5 degrees and the equator, we call this area the tropics, and they receive the most solar radiation, so they get the hottest. Okay. The Arctic Circle is north of 66 degrees of north latitude, and it receives no direct solar radiation in the wintertime. So it's just 24 hours of darkness. I don't know about you, but I'd be very unhappy if I was living in a place like that. And then the Antarctic Circle, that's 66.5 degrees in the south latitudes. That's on the southern hemisphere. Okay, and in addition to that, in addition to the tilting and certain areas of our Earth receiving more or less solar energy depending on where we are in our orbit. There's also an uneven distribution of solar energy based on your latitude. Okay, solar energy is concentrated at lower latitudes. Okay, because there's a high angle of incidence. The best example, the way to kind of show this off is if you have two flashlights. Here's flashlight B and flashlight A, and it's sending its beam of light towards the Earth right around the equator. And if you notice, this beam A passes through kind of this distance of atmosphere and then strikes the Earth directly and leaves kind of like a oval of illumination, let's say. Okay, very tight, small area of illumination. But if you were to have that same flashlight and flash that same beam of light at higher latitudes, so you can see that here, it has to travel through more atmosphere, which means that the solar energy has a higher chance of interacting with particles in the atmosphere or clouds and being deflected, scattered, or reflected. And then when it does strike the surface of the Earth, do you notice how the light shines over a larger area? And so that what that means is that higher latitudes, the light is more diffuse and it's less concentrated because the same amount of light is hitting a larger area. So just imagine holding a flashlight and then straight down on the floor. You have a perfect circle if you're holding it perpendicular to the floor. But as soon as you start turning it up like towards the wall, that same amount of light is going to spread out through a larger distance. And that's why, like, I'm a very fair-skinned person, and I've been to places close to the equator, and I will sunburn very quickly, and that's because of that high concentration of solar radiation coming in and direct into these areas. If you go to higher latitudes, it's a little more diffuse. I would burn, instead of in 5 minutes, maybe 10 minutes. I'm pretty white. Anyways, so the distribution of solar energy varies depending on your latitude. Okay, we mentioned the thickness of the atmosphere varies with latitude with incoming solar radiation. And when you have solar radiation reflect off the Earth's surface, kind of like light coming in and bouncing off of a mirror, we call that albedo. And albedo is just a measurement of what percentage of solar energy is being reflected off the Earth's surface. Okay, average for Earth, if you take into account like what's on the face of the Earth, the oceans, continents, clouds, on average, 30% of the incoming solar radiation is reflected back out into space. Okay, so the average albedo is 30%. But obviously the albedo of different surfaces varies. Okay. And then this table here shows us the percentage of reflection and absorption of solar energy relative to the angle of incidence on the ocean. So let's pretend we're on the surface of the ocean at the equator. That would be here. This is 90 degrees, so we have incoming solar radiation just basically perpendicular to the surface of the ocean, straight down. Only 2% is reflected. 98% of the solar energy is absorbed by the surface of the ocean. So the ocean is taking in a lot of that heat energy. If you go to a different place on Earth, where the sun's rays are coming in at a slight angle, maybe 60 degrees, you still get a lot of absorption. Once you start kind of flattening that angle to 30 degrees, you start to see more reflected radiation. Once you get beyond about 15 degrees, you see this, 20% of the solar energy is reflected outwards. And what this means is that you're approaching the poles. These are higher latitudes, typically. And when you have incoming sunlight coming at a really shallow angle like this, about 40% is reflected away and only 60% is absorbed. And as a result of this, the heat that's stored by ocean water is kind kind of increased at lower latitudes, or oceans in lower latitudes, like in the tropics, they get a net heat gain from solar energy. But if you go to higher latitudes, there's more heat lost than there is gained. Okay, and that's because a number of reasons: the low solar ray incidence, like we talked about, and also a lot of ice typically forms at high latitudes, and ice reflects or has really high albedo. Okay, so if we were to look at the heat gained and lost by the oceans in terms of latitude, these areas in orange are areas where the ocean absorbs more heat than it loses as a result of the incoming solar radiation. So here, this would be considered the entire overall heat budget of our Earth. And so from a little bit past the Tropic of Capricorn in the southern hemisphere to the Tropic of Cancer in the northern hemisphere, maybe like 35 degrees north and south, this is where you have heat gained. Okay, and then in these more northern latitudes in the northern hemisphere and southern hemisphere, you actually get heat loss because of the angle of incidence and diffuse solar energy. All right, so let's talk about the atmosphere, its composition. Every breath you take, our atmosphere on average is made up or composed of nitrogen, 78.1%, then almost 21% oxygen. Okay, and then there are other components. Argon almost makes up a percentage. Okay, then there are other trace gases. Carbon dioxide makes up a very small portion of our atmosphere, but plays a huge role in global weather. And it sits at, right now it's at 0.04%. And that's why it's significant, because it actually traps a lot of infrared radiation or heat. Now, if we look at our atmosphere in terms of its cross-section, so think of like a cake, and you cut a piece of the cake out to see what the layers are. We're going from the surface of the Earth out towards space. So this is altitude in the y-axis. In the x-axis here, we have temperature in Fahrenheit and temperature in Celsius. And our atmosphere is divided up in a number of different levels. Okay, the lowest level, or closest to the surface where most weather occurs, is called the troposphere. And the reason why it's a distinct layer is that throughout the troposphere, temperatures drop as you rise in altitude. And pressure decreases. Temperatures will drop pretty low right around here to the tropopause. Okay, that is a temperature, approximate temperature of what, negative 50 degrees Celsius or negative 76 Fahrenheit. That's very cold. Okay, and then temperatures actually start to increase as you go into the stratosphere. And the reason for this is because there's a molecule in the stratosphere called O3, called ozone. And ozone starts interacting with incoming solar radiation, and it generates heat. And so temperatures kind of stabilize, and they actually increase, and they increase to this area here called the ozone layer. This is where we have the highest concentration of the O3 molecule, and that's where the temperature rises the most. And then this goes on into the upper atmosphere, and temperatures continue to kind of increase slightly and then continue to drop drastically as you approach space. But these are the layers of the Earth. The troposphere extends out 7 miles. Okay. Oh, and the ozone layer is what absorbs UV radiation, harmful UV radiation. So as incoming solar energy comes in, the UV radiation, a big portion of it is absorbed by the O3 molecule in the ozone layer. Okay, so let's talk about the different air masses in our atmosphere. They're distinguished by their density, and so that means is typically they have what makes the density vary is the temperature of those air masses. And so what air masses typically do is kind of begin to move because of these differences in densities and temperatures, and they create circulation cells, and we call those convection cells. Okay, so it's a combination of rising and sinking air. So a convection cell, let's pretend here we're at your studio apartment. There's a very cold window here, and you have a very hot radiator. So this is moving really hot water through the room, and that heats up the air above it. And when you heat up air, you increase its temperature, its density decreases. Density goes down. So because its density goes down, it starts to rise. Then it rises and hits the ceiling and then moves in this direction. And as it moves in this direction, runs into another wall, but then comes into contact with a very cold window. And that lowers the temperature of this warm air. And when you lower the temperature, so if temperature goes down, right, density will go up. God, that's very weird D. Okay, so density goes up, and so the air mass starts to sink. Cooling air sinks, that's the typical rule there. And then as the cool air hits the bottom or the floor, it approaches the hot radiator, and then you've completed that convection cell. So here are the kind of the rules you need to remember. Warm air rises, and that's because it has lower density. Cool air sinks, and that's because it's more dense, kind of like heavier per unit area. Moist air is typically less dense. So moist air, air that has a lot of water vapor in it, typically less dense. And then dry air is typically more dense and associated with high pressured, more dense air. Okay. So the atmospheric water vapor content typically doesn't exceed about 4% of the air mass. But it's the amount of water vapor an air mass can hold depends on the temperature of that air mass. And typically, warm air is typically moist. That's not always the case, but warm air has the potential of holding more moisture than cooler air. So cooler air is typically drier. Okay. So humid air, or air that has a lot of water vapor content in it, is typically less dense than dry air. And that influences the direction of its movement. Okay, so if we talk about, if we think about atmospheric pressure, that is the column of air that sits above your head, and that varies depending on where you are on Earth. If you're at sea level, you typically have high surface pressure, which it equals 1 atmosphere, or 14 pounds per square inch at sea level. But if you go to a different area on Earth, maybe at a higher elevation, the column of air above your head is smaller, and you'll have lower pressure in those areas. Okay, so but that's not always dependent on your altitude, let's say, but air masses that are high pressure and low pressure can move through an area at sea level, and when you have low pressure moving through, that means you have a thin column of air, which means you have lower surface pressure. Okay, and so cool, dense air sinks, okay, which creates higher pressure, so P is higher, and warm, moist air rises, and that means you have low surface pressure. So whenever you have high pressure, you have sinking dry air, typically. Whenever you have low pressure, you have rising warm and moist air. Okay, and so that's what helps create the movement in the atmosphere, is understanding the different air masses we have, different temperatures. If you have a warm air mass, warm rising air, this creates a low pressure system. So that warm air is not very dense, and so it starts to rise, and that creates a low pressure system. So a low pressure system, the molecules here are very far apart from each other. Okay, so that would be an atmospheric low. That creates warm air that rises up into the upper atmosphere. And so what happens is when this warm air rises, this column of warm, less dense air rises, it comes up to cooler areas of the upper atmosphere, and then it begins to cool down, right? As low pressure air moves away, it cools down. And as it cools down, the temperature drops, its density increases, and then it approaches a high pressure system here. And because it got cold and dense, it starts to sink. and as it sinks, it starts colliding with all the other sinking dense air, and then you have the molecules packed together really close together, and those are high pressure systems. And this is what causes our kind of local wind, so to speak, is these convection cells moving from low pressure systems to high pressure systems. And so airflow always flows from high to low pressure systems. Okay, so here's the high pressure system. Here's wind moving on the Earth's surface towards a low pressure system. Okay, and so in order to understand how the atmospheric winds are generated and all the prevailing winds that we're going to talk about, and just understanding how air masses move on the surface of the Earth, we kind of let's initially think about a hypothetical non-spinning Earth. So this is a planet here that's not spinning, so to speak, right? And knowing what we know about convection cells and how air masses behave depending on their temperature and density, what we would expect is at the equator, at low latitudes where there's a lot of solar energy coming in at perpendicular to this planet, it'll heat up the air masses at the equator, make them warm, less dense, and they'll start to rise. So at the equator, these hot air masses will rise and hit the upper atmosphere, and then they'll move towards the poles and cool down as they approach the poles in both hemispheres. And as they approach the pole, they get very cold and dense, and they sink, creating a high pressure system up here, right? Low pressure systems at the equator. And then this air will run along, cool air will run southward along the surface of the Earth as it approaches the hotter latitudes and then heat up again. And that completes kind of a northern hemisphere convection cell, okay, and a southern hemisphere convection cell. Okay, so that's what would happen if we had a non-spinning Earth. But we actually have an Earth that rotates, and so that alters the paths of moving air masses. And one way to understand it is to understand the Coriolis effect. And essentially it's anything with mass that's moving in a direction on a spinning sphere will appear to be deflected from the viewer's perspective. Okay, so imagine you're spinning on one of these playground kind of carousels, I guess, and you're trying to throw a ball to your partner, right? So as you're spinning in a counterclockwise direction, kind of like what the Earth is doing, you throw the ball, but you're throwing the ball to where your partner was because they're rotating away from that direction. So the ball will kind of careen off in a direction, right, where your partner was. And so you kind of have to, in order to for an object to move and hit your intended target, you'd have to kind of throw it ahead of where you'd rotate into. Okay, and the general rule is anything that's moving through latitudes in the northern hemisphere is going to appear like it's deflected to the right, and in the southern hemisphere it appears like it's deflected to the left. And this is directly due to the Earth's rotation. So the Coriolis effect essentially is non-existent at the equator, and that's because if you're kind of moving around on the equator, that latitude is all moving at the same velocity. And if you're just north or south of the equator, the angular velocities of those latitudes, that difference doesn't make, that change in velocity is not that great, so it minimizes the Coriolis effect. But if you're closer to the poles, the Coriolis effect is stronger, okay? And this is, in my opinion, a better way of understanding what the Coriolis effect is that because our Earth is rotating, there's a difference in angular rotational velocity with latitude, right? If you're at the poles, imagine a spinning Earth, right? And you're at the geographic North Pole. You're not spinning because you're at the pole, the actual spot where the Earth is turning around. But as you move away from the pole itself, then you're moving at a velocity because the Earth is rotating. So you're kind of rotating. In one day, it would be 24 hours, but the distance of your rotation is largest at the equator and smallest as you get smaller as you go towards the poles. So that accounts for the different rotational velocities. Okay, so the Coriolis effect is greatest on objects that move long distances across latitudes. So there's no rotational velocity. As soon as you move south along the pole, say you're up here, northern Canada, you're moving at 500 miles an hour. If you're closer to, let's say, Tallahassee, Florida, you'd be moving at approximately 870 miles an hour. And if you're at the equator, you'd be moving the fastest at about 1,000 miles an hour. And the reason is because if you were at the equator, this distance traveled over a 24-hour period would be the largest. Right? Because on a sphere, the equator is kind of like the bulgiest point on our Earth. So that distance, all of these areas, like regardless of wherever you are on this latitude or here, in 24 hours you're rotating 360 degrees. But this distance is a lot smaller in comparison to the distance you'd be traveling if you were at the equator. Therefore, you're moving at a faster velocity at the equator. Okay? And so, in the book, there's some sort of hypothetical war. New Orleans is really pissed off some people here in northern Canada and also people in the Galapagos. And so they're firing missiles towards New Orleans. Not sure why. But, so what happens here is the Galapagos Islands is near the equator, and they fire their missile, right? And if they fire their missile, because they're moving at a faster angular velocity than New Orleans, and in the northern hemisphere, it'll appear like the missile's deflected to the right because it's being shot from an area that's rotating faster than New Orleans is at this latitude. So it's almost like you could launch the missile and then it can hang out up in the air for a while and wait till New Orleans rotates into the spot where it's supposed to land. Kind of understand what I'm saying here? So the deflection is to the right, okay? But if a missile is flying southbound, the Coriolis effect is greater because it's closer to the poles, and because, say you're launching from northern Canada, you're launching from an area that has lower velocity. So New Orleans is actually rotating faster than this area here. So as you shoot the missile southbound, it appears to get deflected to the right, and that's because this area has kind of moved out of the way if you were flying it in a straight path. Obviously, we have technology to make adjustments for the Coriolis effect, and those missiles would land a little closer to New Orleans. But that's the Coriolis effect, and the reason why we talk about it is because the Coriolis effect, like how it appears to deflect the path of missiles, air masses that move across latitude areas on the Earth, on the surface of the Earth, are going to be deflected to the right in the northern hemisphere and deflected to the left in the southern hemisphere. Okay, so it has a huge influence. Okay, so now we're going to start understanding the global atmospheric circulation. And there are three main circulation cells. So in that hypothetical non-spinning Earth, there was only two, but we know we live on a spinning Earth. So there are three circulation cells. There's the Hadley cell, and that is from the equator to about 30 degrees, or the horse latitudes. Okay, and that's what you see pictured down here. We have really low, hot pressure, equatorial air rising, low density, receiving a lot of solar radiation, going up to the upper atmosphere and then traveling into the northern hemisphere and then also into the southern hemisphere, cooling down and then sinking at these subtropical high pressure zones. And then it kind of goes down towards the equator again, and this is what creates these wind belts called the trade winds. Trade winds north and south of the equator will be over here. All right, and then beyond 30 degrees north and south of the equator to about 60 degrees are Ferrel cells. William Ferrel was the scientist who came up with this. And then beyond 60 degrees north and south of the equator, there are polar cells. Okay, and that rising and descending air, that's what generates those low pressure and high pressure zones. Okay, so this is the equator and this is the subtropics north and south of the equator. So here, I really like this. This GIF shows you well, at least it just shows you the Hadley cells, which are close to the equator, right? Here's the equator. We have low pressure systems here, and that receives a lot of solar radiation. You have a lot of rising warm air, hits the upper atmosphere, cools down, and then descends towards the Earth at these high pressure zones here. Okay, and then as these air, as this air moves back towards the equator, heats up, that completes that convection cell. But if you notice, okay, the air that moves kind of like northward from the southern hemisphere to the equator, or southward from these descending high pressure system areas here, they're going to be deflected to the right in the northern hemisphere, and that's what creates the northeastern trade winds right there. Okay, so that's what the prevailing winds are in each one of these cells. Okay, so we have the southern moving air that's warming up getting deflected to the right. That creates the trade winds. And in the southern hemisphere, this stuff is moving northward, but then it's deflected to the left because it's the southern hemisphere, and that creates the southeastern trade winds. Okay. And so what you see at these high pressure zones, which are here, right? This is a high pressure zone where we have a lot of descending air from the upper atmosphere. That typically happens at 30 degrees latitude. And that means a lot of dry, cold air descends towards the Earth in these areas. Okay, here, and then also in these latitudes in the southern hemisphere. You have your high pressure systems here. So though we call those subtropical highs. Then if we go further, there's another circulation cell here. I'll show you in the next slide, and another here. Another prominent high pressure system is right here at the poles. We call those the polar highs, and that happens at 90 degrees latitude. And what you typically see in these high pressure systems are clear skies and very dry air. Okay, so to even complicate matters, as you well know, orbit the sun, our seasons kind of push the zones or the cells, or kind of shrinks them or enlarges them depending on what season we're in. So the GIF that you see here are the kind of shifting Hadley, Ferrel, and polar cells up and down with the seasons. But you can see them three-dimensionally here. So now this is going to be hard to do. This here and this cell here are the Hadley cells. Then we have the Ferrel cells here. Okay. And then so some of these cells generate low pressure zones. So the low pressure zones would be found closer to the equator here. And then over here, these would be low pressure zones as well. Okay. So the low pressure zone at the equator is called the equatorial low. And then up here, right around 60 degrees of latitude, we call those the subpolar lows. And what you typically see here are overcast skies with a lot of precipitation. Okay, and there it is. This is the 3-cell model of our atmospheric circulation. So we have the two Hadley cells here, right? And here we have rising warm air at the equators, cools down, and then sinks at those horse latitudes or subtropical highs. Okay, then that air kind of moves northward here and is deflected to the left in the southern hemisphere, moves southward in the northern hemisphere and is deflected to the right. And this creates the prevailing winds, the trade winds, the northeast trade winds here and here. And the northeast trade winds is what Columbus rode from Europe all the way to the Caribbean. Okay, then we have the Ferrel cells here, where you have air moving on the surface northward. Again, these are the prevailing westerlies. They're deflected to the right in the northern hemisphere. So the prevailing winds are moving in a westerly direction. But then they reach the kind of the polar front here, and they start to rise as a low pressure system. Okay, and that completes this cell. And then here's the polar highs. Okay, so here's a high, and then anywhere we see the rising warmer air would be a low. Okay, so here are the highs. There you go. This is our, think of it three-dimensionally with winds on the surface and winds in the upper atmosphere. This is our 3-cell model of atmospheric circulation. And that's what generates our global wind belts. And in turn, those wind belts is what pushes ocean currents. Okay. So the trade winds, as I mentioned, they're from the subtropical highs to the equator. There's the northeast trade winds in the northern hemisphere, the southeast trade winds in the southern hemisphere, and they blow, these prevailing winds blow from the east towards the west. Okay, then there's north of that from 30 to 60 degrees north and south of the equator, there are the prevailing westerly wind belts, and they blow in the other direction from west towards east. Okay. And then there's the polar easterly wind belts, which are further north, 60 to 90 degrees latitude. And then in between those major wind belts, there are the doldrums, or the intertropical convergence zone. That's directly at the equator. They call it, or sailors named it the doldrums because initially they depended on wind to kind of, and their sails to be, the wind to push their boats to different locations, and if they were in or at the equator, there's the wind kind of dies down, and then so they would be stranded, and so that's why it's kind of referred to as the doldrums. The horse latitudes were, which is pretty close to Florida. This typically the weather here is very clear, dry, and fair. Most of the world's deserts are found on the horse latitudes, and that's because of that descending cold air from the upper atmosphere has very little moisture, and so that affects local climate. Okay, and then there's the polar front, where you have very cloudy, overcast skies, a lot of precipitation, and because of colliding air masses. So think of like a dreary London with a lot of gray skies and rain. And that's because they're closer to the polar front. Okay, so here are all the different regions, latitudes on Earth with the name of the predominant wind belt or boundary, the atmospheric pressure, and their characteristics. So this is good review before a quiz, knowing the predominant winds in each latitude. And so this is a typical this is real data collected in January showing the different high pressure systems along with the prevailing winds. So here are the trade winds you can see here, right? Here are the prevailing westerlies blowing in the opposite direction. Okay, so you can see that. Here's the equatorial doldrums. Some high pressure systems kind of drives local wind, which may be opposite to the prevailing winds. So that can happen. In reality, the three kind of convection cell model is just complicated by ocean currents, the different land masses that are in the way because land has different heat capacity than water does. So it can be more complex in reality. The tilt of the Earth and the seasons kind of push the boundaries up and down depending on what the seasons are. I mentioned the lower heat capacity when you compare land to seawater. And then there's uneven distribution of land and ocean. Like, for example, in the southern hemisphere, there's a lot more ocean than there is land in comparison to the northern hemisphere. So that affects atmospheric wind belts. All right, so there's a difference between weather and climate. Weather are the conditions of an atmosphere in a particular time or place. Climate is more of a long-term average of weather. And the ocean, or our ocean, influences our weather and climate patterns, especially here in Florida. All right, so localized winds, can be generated by cyclonic or anticyclonic flow. So in the northern hemisphere where we're located, if you have cyclonic flow, that's counterclockwise, and that's typically here. This is your counterclockwise flow in a low pressure system, right? So remember, low pressure systems, you have warm, less dense air rising. And what happens is winds flow from high pressure systems towards low pressure systems. And so when winds approach a low pressure system in the northern hemisphere, they get deflected to the right. And so that's why this is that right deflection, deflection to the right, deflection to the right. And what it ends up resulting in is counterclockwise spinning or flowing, right? And this is why hurricanes, which are low pressure systems in the northern hemisphere, rotate in a counterclockwise direction. So imagine this screw kind of rotating in a counterclockwise direction. Okay, anticyclonic flow are these high pressure systems, right? High pressure systems, you typically have more dense, colder air descending from the upper atmosphere, and as it descends, it kind of moves away from the high pressure system. So it's this generates wind on the surface moving away from the high pressure system. In the northern hemisphere, if you have any air mass moving in a certain direction, it's going to be deflected to the right. So here you can see deflection to the right, deflection to the right, deflection to the right. And then if you notice, that is clockwise rotation. So that's typical localized winds. If you have a high pressure system, you have rotating winds in a clockwise direction. Now, if you're in the southern hemisphere, everything's reverse. So low pressure systems actually go clockwise, and high pressure systems are counterclockwise. So here's your typical weather map showing kind of the local wind flow patterns relative to high and low pressure systems. So here is a low pressure system rotating counterclockwise, and here's a high one rotating in a clockwise direction. And then there are differences in solar heating from the ocean surface to land, and this causes kind of localized changes in air patterns or wind distribution. So what happens is a sea breeze, which I'm sure you're used to here in Florida. What happens when you have a sea breeze is because the air masses that are sitting above the ocean don't heat up as quickly as air masses sitting over land. The air masses over land get hot on a hot sunny day, and causes that the air masses sitting above land, because the heat capacity is lower, it transfers the heat off the land into the air masses above, heats up those air masses, and it rises. And then cooler ocean air comes in to replace it. And that's why, say you live in like inland Florida or central Florida, it's always a few degrees warmer in central Florida when you compare to the coasts, because the coasts are their local climate is influenced by cooler sea breeze airs that kind of move in towards the inland areas of Florida. And then the opposite can happen too. This will happen because the oceans tend to hold on to a lot of heat, so their temperatures won't fluctuate that much. So if it's very cold out, the air masses over land get colder much faster than the air masses over the water. So then you can actually get a land breeze where cooler air moves out towards the ocean. Okay, and then there are storms and our local kind of crazy weather that can occur. That is the result of air masses kind of interacting with one another. Okay, a storm is a disturbance with very strong winds and precipitation. Okay, and this occurs because air masses, which are large volumes of air with distinct properties, typically differences in temperature, which are almost synonymous with changes in density, and also whether or not they have water vapor in them. Okay, typically land air masses are dry, and then air masses that are over the ocean are moist. They have a lot more moisture because they're interacting with the ocean water. So if we take a look at our globe, here are the different air masses. Okay, Blue denotes the temperature. So these are typically cooler air masses because they originate, or their origin is at higher latitudes. Over here we have red air masses that form in different areas. Red meaning that they're typically warmer. Okay, but if they originate over water, like this one does, this is a maritime tropical air mass. It's given that M sub T notation. That is a warm and moist air mass, right? And it typically moves in this direction, right? You can have air masses from lower latitudes that originate over land. We call those continental tropical air masses. And these are typically warm and dry, okay? Same thing goes for cooler air masses. If they originate over the ocean, then they're cool and moist. And if they originate over land, like this continental polar air mass, that means they're cold and dry. And so what happens, what creates storms and kind of local changes in weather are air masses kind of moving in through an area, and they kind of collide with each other. Because air masses don't really mix. Because they have different temperatures and therefore different densities, what will happen is the lower density air mass will be kind of pushed above the higher density air mass, and that creates a front. A front is a boundary between those air masses because they don't mix very well. So our first example is an example of a warm front. And what happens with a warm front is that you have a warm air mass moving in this direction, and it collides with a colder air mass. So because the colder air mass is more dense, it basically pushes the warm air mass upwards. And as the warm air mass is pushed upwards, all the moisture it contains condenses because it cools down, and then you get rain, and you have this kind of gradual slope of warm air being pushed above the cold air, and then you have moderate rain. The clouds get higher and higher, or as if you're sitting here and the frontal boundary is moving in this direction, the clouds will become lower and lower as the warm air mass approaches. Okay, a cold front is when you have a very cold air mass, and this is moving, into an area like a freight train just bashing its way through. This forces the warm air up very rapidly along this steep slope up to the higher into the atmosphere, causing all its moisture to condense, and then you get heavy rainfall. And cold air masses a lot of times are associated with thunderstorms. And what will happen is you'll get very intense rain, but then as the cold air moves through, then you'll have clear skies behind it. Okay, and so that's what drives a lot of weather in areas in the United States. In addition to that, the jet stream is this narrow, fast-moving, almost like river of air in the upper atmosphere. And at mid-latitudes, it's just below the troposphere, and it has this kind of wavy type shape, and it on a yearly basis alters or kind of varies, and that has the potential of pushing air masses in certain directions. It can kind of steer some of those really cold air masses, especially during the winter, down south towards areas like Florida, and we can get massive cold fronts as a result of that. All right, let's talk about hurricanes or tropical cyclones. These are large rotating masses of low pressure. I'm sure many of you are familiar with this from personal experience. Strong winds, torrential rain coming sideways up into all the cracks into your house, maybe even coming into your house and you're freaking out, These hurricanes are classified based on the maximum sustained wind speed. Okay, there are tropical cyclones all over the world. We call them hurricanes. In the North Pacific, they're referred to as typhoons, and in the Indian Ocean, they're called cyclones. All right, so the origins of a hurricane, you might know from watching kind of local weather, but they'll typically show you places out in the Atlantic Ocean basin near the equator. And it's typically like a low pressure cell that has the chance of forming a low pressure system and start to intensify. And so what happens is in that doldrum area of the equator, you have very hot and rising air, and that wind feeds water vapor into that low pressure system. and then that water vapor condenses when it rises up. Um, uh, uh, it condenses, and then that latent heat of condensation, I don't know if you remember that from a previous lecture, but heat is released. And as that heat is released, it heats up the air around it, which causes more rising air and faster rising air, which brings in more water vapor. And that's how hurricanes or low pressure systems intensify eventually into hurricanes. So the pressure deepens, and then storm develops. Okay, so if you go from a low pressure system to a tropical depression, that's when your sustained winds are less than 38 miles an hour. When it's upgraded to a tropical storm, that means its range of sustained winds is 38 to 74. And once you exceed 74 mile an hour, then sustained winds, then you're in the hurricane territory. And then this is the Saffir-Simpson hurricane intensity scale from category 1 to 5. I'm sure you guys are very familiar, but yeah, you can go from 100 or 74 miles an hour to being a category 1 to greater than 155 miles an hour with a category 5, which is pretty crazy. Not a lot of people talk about this, but this is incredibly important and causes a lot of damage to coastal areas, but is the storm surge. So essentially these low pressure systems or hurricanes are rotating in a counterclockwise fashion, and the air is rising. So what that does is that raises sea level because of that. It's almost like holding a vacuum cleaner above like an aquarium. As it sucks that air upwards, it's going to lift the water level up. And that can cause flooding because sea level can rise in worst case scenario, category 5, greater than 19 feet. That's 2 basketball hoops stacked on top of each other. So that can be catastrophic to a lot of these coastal communities. So we have about 100 hurricanes a year, and for their formation, they require really warm ocean water above 25 degrees Celsius or 77 degrees Fahrenheit. Warm, moist air, and the Coriolis effect helps kind of guide them, right? Or kind of deflects them in certain directions. And our hurricane season is from June 1st to November 30th. This is all hurricane or tropical cyclone tracks across the Pacific, Atlantic, and Indian Ocean basins over the past 150 years. If you notice, a lot of their tracks in the northern hemisphere, they move this way and then they curve upwards. That's the Coriolis effect, right? Northern hemisphere, it curves to the right. In the southern hemisphere, you can see they curve to the left. They come in and curve downward. And here, this is where we usually deal with them, and they usually come in and curve to the right. So let's look at a hurricane, the diameter, the anatomy of a hurricane. So this is, if you were kind of to cut a hurricane in half, this is what it would look like, its innards. The diameter is typically less than 124 miles, but this sadly is becoming less and less true. There are larger and larger storms forming. They can be as large as 500 miles in diameter. Think about that. That's from like Miami to Jacksonville. So that can be the entire diameter of a hurricane. There have been some really big ones, pretty scary. But again, like I was talking about, they have circulating winds. It's a low pressure system, so you have rising air that's kind of spiraling upwards, right? And all the air from the surrounding regions are moving towards this low pressure system, and as they do, they get deflected to the right, right? And then they get caught up in this spinning high sustained winds. And then right at the eye, you have, this is the low pressure center of the storm. And right at the eye, you have warmer descending air. And I don't know if you've ever experienced the eye of a hurricane, but it's very bizarre because a lot of times the clouds will clear and you can actually see the sun. There isn't any rain, there's no wind. So it's kind of bizarre. And then you get hit the next eye wall. And then the worst winds are at the eye wall, which is right over here. They have the maximum sustained winds. Okay, so how do hurricanes move? Well, they get pushed around by the prevailing winds. So the trade winds, which we just learned about, right? Those prevailing winds blow in this direction. So when we have low pressure systems developing, As they move, they get pushed by the trade winds. They have that apparent deflection from the Coriolis effect, and if they get just north enough, then they can be pushed back out into the Atlantic Ocean by the prevailing westerlies. So it's a combination of the prevailing winds and at differing latitudes, and also the Coriolis effect. There are a lot of other effects, like the jet stream can affect the path of a hurricane. There's a whole science to it, and that's how they come up with those spaghetti models and predict the path of hurricanes. So we're just kind of skimming the surface there. Warmer waters in the ocean favor hurricane development. So that's what a big problem is with global warming. We're putting a lot of CO2 in the atmosphere. CO2 is a greenhouse gas, and it helps trap a lot of heat in our atmosphere. So our atmospheres are getting warmer, which means our oceans are also getting warmer and absorbing more heat. And if our oceans' sea surface temperatures are higher, that's going to favor hurricane development and intensification. So I think scientists today aren't predicting that every hurricane season there are going to be more hurricanes. They are predicting, however, that the hurricanes will intensify, or Category 4, 3, 4, and 5 hurricanes are going to occur more often because of warmer sea surface temperatures. Okay. Wind shear also impacts the movement of a hurricane. So if you have different low pressure or high pressure systems kind of moving around in the area, that can impact where the path of the hurricane can move. Then there's other factors. There's an oscillation in the Pacific Ocean, atmospheric oscillation, and there's some interesting weather occurrences that occur there, cyclonic stuff called El Nino and La Nina. That can also affect how our hurricane seasons in Florida, but we'll cover that in the next chapter. Hurricane destruction can be devastating. High winds can topple over a lot of structures, cause a lot of property damage, and loss of life. Intense rainfall and flooding is very destructive as well. I mean, hurricane rain basically comes at you at really high speeds, and it's like a horizontal rain, so it can get into any crevice or crack in your house if it's not sealed properly. So that's pretty dangerous. But the most dangerous aspect of hurricanes is a storm surge, like we talked about. The storm surge increases sea level, typically in this kind of northwestern quadrant. See, in the northern hemisphere, here's the rotating low pressure system. This is the worst area to be. They have the strongest winds, the eye wall is the strongest, and also the highest storm surge. And so when you have a storm surge of like over 19 feet, that's going to flood a lot of coastal areas, especially in Florida, because a lot of those areas aren't built up very high. All right, so some of the most historic and destructive storms, those Galveston in 1900 that killed thousands of people. Galveston is like a barrier island off the coast of Texas near Houston. And this is in 1900. This is before we could warn people with satellites. So people there were just completely caught by surprise and then dealt with a really strong hurricane. Hurricane Andrew in 1992 in South Florida was huge. Another notable one we'll talk about is Katrina in 2005. Absolute devastation in Louisiana and a lot of Gulf Coast states like Mississippi. There was Irene and Sandy. More recently, we had Irma tear through Central Florida. So, yeah, all right. Sandy's mentioned because it hit the Northeast, and a lot of people live up there. It was a Category 1 as it approached the Northeast, and it diminished to tropical storm. But the storm surge coincided with high tide in New York and New Jersey, which caused severe flooding and coastal erosion. There were 233 deaths and more than $68 billion of damage. So second costliest after Katrina. Right, here is the boardwalk in New Jersey. Oh my God, get some water ice. And then there's the 2005 Atlantic hurricane season. I don't know if many of you experienced this, but this one was the most active on record. 27 named storms, 15 became hurricanes. The season went into January. There were 5 Category 4 or 5 storms. Dennis, Emily, Katrina, Wilma ravaged Southwest Florida and the Fort Lauderdale area. I was in Fort Lauderdale at the time, so it's pretty bad. And then there was Katrina, right? Katrina was the costliest and deadliest U.S. hurricane. Katrina was interesting because it kind of hit South Florida as a Category 1, went into the Gulf, intensified, and then struck New Orleans and Mississippi. But New Orleans is very susceptible to flooding already. I mean, many portions of the town are below sea level, and they have levees to prevent flooding. So when all of this rain and high winds came in, it broke a lot of levees, caused massive flooding, and there was a pretty terrible response to this. There's a lot of people who lost their homes, mass homelessness, and a lot of people died from being stranded out there. So yeah, Katrina was really awful for New Orleans. Other notable ones: Rita in 2005. That was the most intense Gulf of Mexico tropical cyclone. There was a lot of damage in Texas, Louisiana. Wilma, like I said, that affected 11 countries, multiple landfalls. And in the future, hurricanes are going to pose a continual threat to coastal communities. Loss of life is decreasing because of our better forecasts and evacuation. We meteorologists do a really good job of developing all the potential areas a hurricane can move into, and the closer a hurricane gets, then they can kind of narrow down the areas that are threatened, and they really give out good information on how much storm surge there'll be, the maximum sustained winds. They do a really good job so that it helps people make the right decision in order to evacuate or stay put in their homes, and that really saves lives. Even though loss of life has been decreasing, the loss in property has been increasing because most people want to move near the coastline because the weather is great and it's beautiful, right? And people want to live there, but it comes with dangers like storm surge. Okay, so our climate patterns, our open ocean has certain climate regions, and they're really parallel to latitude lines. And these regions can be expanded or minimized based on surface ocean currents. Okay, so for example, here are different climate regions. Equatorial is anywhere in this red area here, right? Very warm, rising air, lots of precipitation. Then there's the tropical area here, right? Outlined and here. And if you notice, because of warm ocean currents, it pushes this tropical weather pattern to higher latitudes than over here because there's colder ocean water pushing the climate region downwards. We'll talk about this when we talk about ocean currents. But there it is, and then there's the subpolar, the temperate, and then the polar climate regions. Okay, so the equatorial climate regions, typical rising air, very weak winds, that's where the doldrums are, lots of precipitation, very hot. Then there's the tropical. This goes from the tropics of Cancer and Capricorn. Very strong winds, little precipitation, and very rough seas. All right, then there's a subtropical ocean climate zone, which is where you have high pressure, descending cool air, very weak winds, and sluggish currents. And then in the temperate areas, so think of like latitudes where New York, Philadelphia, Boston are, you have a lot of strong westerly winds, and severe storms are very common in the ocean. Then there's a subpolar where there's a lot of rain. Think of kind of latitudes of Iceland or London or something, Northern Europe. You have extensive precipitation, and in the oceans, you can have summer sea ice. And then in polar regions, high pressure systems, typically dry, very cold air descending down towards the surface. And here in the oceans, you have sea ice most of the year. Okay, and then lastly, really, a lot of energy can be generated from wind itself, right? So as the solar energy kind of strikes the Earth, that starts the kind of atmospheric engine, and winds are generated and move across the surface of the Earth. Well, we can take advantage of that, and we can put turbines in latitudes of our Earth where we know there are very strong and prevailing winds. And so these offshore wind farms can generate a lot of electricity. And the cool thing about it is that it's renewable, meaning that every single day the wind's going to blow and it's going to generate electricity. And that's fantastic because there's no waste product, right? There's no pumping CO2 in the atmosphere. So this slide here shows the potential areas where there's a lot of wind or prevailing winds that can be taken advantage of and used with these wind farms. Sometimes the big problem is that a lot of times they're in the middle of the ocean, so it's almost impossible to build something way out here. So typically it's convenient if they're very close to land, because then we can transfer the power over to areas that need it. But yeah, so the global ocean wind energy is an area that can be tapped and used, and it's great renewable resource for humans.